which is called flashback recorder, and does quite a nice job of recording. Lets me edit, insert other pointers and stuff like that. So that's what I use to put all the stuff up on YouTube. Okay, so if you load that Goodwin O2 model, let's go back and I'll get to that point. Let's see. Okay. So you have that model running. What I'll do is go to it myself and show you how to endogenize the rate of growth of labour productivity and the rate of growth of population. So that's the A and the N here. So drag them over somewhere else on the canvas. Right click on A. First you've got to turn it into a variable, which is called a flow. And the same thing for N. Okay. Then having done that, right click on them and choose Add Integral. Then you need rates of change, so I use alpha for technical change and beta for population. So / alpha will give you the Greek alpha. Make that into a parameter. I'll give it a value of 0.015. I won't bother with the maximum minimum now, I'll just get them set up quickly. That's alpha. Then you want a beta as well, so / beta for beta. Make that 0.02, high rate of population growth. Got to make it into a parameter, I'll just roughly do that. Am I recording this? Yes, I am, good. Okay, so now I've got alpha and beta, and I need an A0 and an N0, so A_0 will give you that subscript 0. And thank you. And make that, say, 1 worker per unit of output. And then an N0, so N, capital N_0, make it 120. And then you've got all your, again, I forgot to make that into a parameter. Not that it's essential, it's just being neat and tidy.
What's the initial value for A?
1, just one would be fine. So then you've attached the initial value to the bottom of the integral sign. Take a copy of A, multiply that by alpha. I'll just take a copy of alpha just to have it sitting up there. Multiply A by alpha, integrate it, you have A, that's the percentage rate of change function. And the same thing for population, so beta multiplied by N, integrated is level of population. Click stop and then run, and you've got a functional model which will have steeper parameters because you're actually changing the period and the amplitude to some extent by adding those functions inside there. Okay? All got? Okay, so that's stage 1. Now I've got to ask a very important question just before we finished about the cycles. Why does it cycle all the time? And Marx was right about this, so it's quite intriguing. His verbal intuition was that, this is what we've just now shown you how to do, adding the integral and so on. His verbal intuition was quite accurate, which is remarkable. Okay, I very rarely find that an economist's verbal intuition is actually correct. The only person I know that does all the time seems to be Schumpeter. So those were given the growth rates, and what I want to show you now very quickly is defining a rate of growth, because as we work in integral blocks, but once you've got something integrated, then you can differentiate it and get a rate of growth out of it. So what I want to do is add a rate of growth, actually get a formal definition of the rate of growth there. So I have y, which is changing through time, of course. How fast is it changing? You feed y into a DDT block, you get the rate of change of y. You divide that by itself, that's the fractional rate of change. You multiply it by 100, you get the growth rate in percentages. Okay? So let's take a look at that. And I'll just zoom in over here. Notice on the blocks over here, you've got an integral block up there, And I'm desperately trying to find the differential block now. Where's it been? This is version. Here we are at the very end. There's the differential block. So if I click on that and bring it down here, I'll make it a bit larger. If you just press the plus key on the zoom to make things a bit larger so you can see what you're doing, hold the shift key and drag the whole simulation over. So when I have Y, I'm going to go back out again and find Y, copy Y, bring it down here, zoom back in again. So feed Y into the dy dt block, divide by Y, divide the rate of change by the current value, which gives me a percentage rate. And I want to create a parameter. Again, keep getting confused between versions of parameter, called percentage, which has a value of 100 and a maximum of 100 and a minimum of 100 and a step size of 0. In other words, you can't change percentages. Okay, just make it rigid there. So you then drag that onto the multiply block. You can have more than one thing on the multiply block, and call this G underscore R for growth rate. Wire that up, you've now got a growth rate. So we go back, and I'll take a copy of growth rate, bring it over here, go back to the normal scale. Let's put the growth rate down here, let's say. Put another graph in. I'll make that red just for the heck of it. This is the old version. We've changed how we resize from the version 2.15 to 2.15.8. In the old version you had to right click and then choose resize with a rubber band, but it was really hard to align stuff. So in the new version, that's why those 4 arrows are there, to let you align things more evenly. But now when I run this, I can see the growth rate in percentage terms as well. Okay? And let's actually look at Y as well. So you take a copy of Y and whack a graph of Y there. You can get carried away with graphs and things like Minsky because it's just so easy to whack them in. At some point, if you want to make this more visible to other people, then you'd need to organise things using bookmarks, and I'll show you that in a moment. So if you think about the units of GDP, it's widgets per year. So that now gives me a graph. Let's make it a bit larger. So what you've got is cyclical growth, okay? Booms and slumps. It's pretty amazing for Marx to get that right verbally in 1867. Okay, so there's a strong intuition there. And that's important because one of the guys that Marx was an influence on was Hyman Minsky. Okay? There's actually a funny little story about that. I met Minsky once when I was doing my PhD. He wasn't exactly communicative. He wrote to me once when he saw my paper in 95. I wrote back saying I wanted to integrate Marx with post-Keynesian economics. He never wrote to me again. I've ended up doing it anyway. But he had a difficult relationship with his son for a while, and they reconciled in their 30s. This happens to almost all families, I'm sure. I can say the same thing for my family. And Alan, who went into independent media, the precursor of social media, rather than economics. And then in his 30s, started to get on better with his dad. And this is Alan telling me the story. He asked his father, what book should I read first to understand economics? And this was, remember, Minsky was raised in the 20s and 30s. He lived through the 40s, 50s and 60s, the McCarthyist period. If you even admitted that you'd seen a copy of Das Kapital, you'd lose a job at an American university, land of the free not to read stuff we don't want you to read. Anyway, he goes into his study, and Alan showed the mannerism. He goes and he comes out, says, this is the book you should read. It was a copy of Das Kapital, Volume 1. So you won't find a single reference to Marx in Minsky's writings, but Marx was a major influence. And I see the tie between Marx having this vision, in Goodwin having the cyclical models as well, Marx was also an inspiration for Goodwin, a very important inspiration. Goodwin did call himself a Marxist. He had no qualms about saying that sort of thing. But a lot of the vision that you'll find in Minsky comes from Marx, intriguingly enough. Anyway, so back over here. So we've got a growth rate defined now. And that's, again, the cyclical model that I've shown you a moment ago. So what causes the cycles? Your question. And mathematically, you have an equilibrium which is neutral. It neither attracts nor repels the system. Now, neoclassicals never ask, this is one of Yanis Varoufakis' very good points in characterising what defines neoclassical economics, and it's ignoring the question of whether equilibrium is stable or not. Okay? Frequently, their equilibria are unstable. So the equilibrium of a Walrasian system is unstable. The equilibrium of Ramsey's growth model is unstable. But they force stability on it by mad assumptions. So the mad assumption in the Ramsey model, which gives them their so-called trade cycle, is what they call a jump variable. We can instantly decide to consume less, so we jump from one particular path onto the saddle node that'll give us the fluctuations that lead to equilibrium. All this magical nonsense stuff they do that they call mathematical modelling. And if they ever hear about Goodwin, they deride Goodwin as being ad hoc, with this constant relationship with labour and capital. Why haven't you got a variable production function, yada, yada, yada? Well, you can actually derive Minsky Goodwin directly from macroeconomic definitions. So I'm going to take you through a second way of defining Goodwin, and then we can answer your question about stability. So if you define the employment rate as the number of people with a job divided by population, it's rather hard to disagree with the definition, isn't it? That's the definition. If you define the wages share of output as wages divided by GDP, that's the definition. Equally, if I define labour productivity as output divided by workers, that's the definition. So I'm working from definitions. And if you differentiate those, you can find yourself getting a dynamic version of a definition. So if you don't disagree with the definition, you can't disagree with the dynamic definition either. Okay? And this is like neoclassicals, always they want to have good foundations. Well, they do, their micro is nonsense anyway. And you look at whether firms have rising marginal costs. No, they don't. Whether perfect competition can be a perfect. No, it can't. Whether consumers maximise utility. No, they don't, etc., etc. It's all mythical. But they work from that foundation up. They ignore an aggregation problem called the Sonnenschein-Mantel-de-Breuer theorem, which says they can't derive market demand curves from individual demand curves, all this sort of stuff. So they think they've got great foundations. They haven't. But good foundations are a good idea. So what I want to show you is Goodwin is based on the best possible foundations. You can derive it directly from macroeconomic definitions. So the shortcut I'm going to show you is, this is one of my mathematician friends does this, the difference between a mathematician and a person like myself doing mathematical economics is a mathematician does stuff the easy way. Okay? So as soon as Matthias sees an expression like 1 over x dx dt equals L divided by n, he simply says you can simply expand it out and say the rate of change of the labour employment rate is the rate of change of labour divided by the rate of change of population. A simple expression. I do the laborious stuff, but I'll show you. You start by saying the hat means 1 over x dx dt. Okay? So the hat means 1 over lambda dt, which is the percentage rate of growth of the employment rate, which is the employment rate is L over n. Okay? So you can simply say it's the percentage rate of growth of employment minus the percentage rate of growth of population. That's mathematically correct. Just get this in an instant. And then your definition of labour is the output divided by labour productivity. That you can also expand out. So very rapidly you can say the rate of change of the employment rate is the rate of growth minus the rate of technical change minus the rate of growth of population. And that is still the definition. Okay, it's not a model yet, it's strictly true. So long as you use those definitions. Okay? Now that's the long way of doing it. I get to the same basic point. It's more laborious, but basically that's a shortcut you can use and reliably know it's going to be right 100% of the time. That's still the definition of what it says is the employment rate will grow if economic growth exceeds the sum of labour productivity and population growth. So that is still a strictly true statement. Okay, there it is. Now, for the wage share is total wages divided by output, where total wages, we're making a bit of an assumption here. We're saying there's a uniform real wage. Okay, so that's why I'm using an equal sign here rather than using a definition sign. Okay, so there are some assumptions coming at this stage. So you can simplify that, because your total wage bill you are assuming is total labour multiplied by uniform wage rate. Your labour productivity definition output is labour multiplied by labour productivity. The two L's cancel, and what you get finally is an expression in the wage rate divided by labour productivity. So then you can say the rate of change of the wages share is the rate of change of wages, and you're not having any model about how that occurs, minus the rate of growth of labour productivity. So that says the wages share of GDP will rise if wage rises exceed productivity growth. That's also, given a couple of assumptions, a factually true statement. You measure it in the national accounts, that's what you'll find. So those are your dynamic definitions. To make it into a model, you have to add some assumptions here. And I'm going to simply assume that there's exogenous population growth, which is what we had in the model you built, giving the circular definition. Exogenous productivity growth, same as the previous model. A fixed capital output ratio. I'm not worried about capacity utilisation here. You can bring that in later. That's a sort of embellishment you do to make the models more realistic. Investment being profit minus depreciation. Now we're going to generalise that very shortly, but that's exactly the same as the previous model. And a linear Phillips curve. Those are my assumptions. Now when you put them all together, I'll do a bit of explanation here. I'm using linear terms, but neoclassicals often think your model's unstable because you're using a linear function. No, moron. Pardon me, but I can't. I'm getting less polite as I get older, and that's saying something. A linear model is the first approximation of any nonlinear model. And if you want to know what's going to happen near the equilibrium of a system, it's the linear term that dominates. So if you're trying to characterise, if you have an equilibrium which is unstable, you can't stabilise it by adding nonlinear terms. It'll still be unstable, because the linear term close to the equilibrium is bigger than the nonlinear terms. If you take a function which is nonlinear, like a Cobb-Douglas reduction function, for example, and you want to break that down into a series of polynomials, you'll have a constant plus a parameter times x plus a parameter times x squared, etc., etc. If you're close to the equilibrium, x is going to be bigger than x squared and bigger than x cubed, etc., etc. So the linear term dominates. So you can't stabilise an unstable model by adding nonlinear terms to it. It'll still be unstable around the equilibrium. The nonlinear terms will change its behaviour away from the equilibrium. They won't make the equilibrium more stable. So we have this definition here. So I'm just going to expand it out. So I have the rate of change of the employment rate is the rate of change of capital stock divided by the accelerator. That's my substitution for rate of change of output up there, minus alpha minus beta. We know this is 1 over kd kdt, which is profit, because we're assuming all profits are invested, minus depreciation divided by the capital stock. The capital stock is V times the output level. We now have Y, which we can divide through and get 1 there. This is W divided by Y, which is omega. So my overall expression for the rate of change of the employment rate is 1 minus the wages share divided by V minus depreciation, and I've left out the alpha and beta. Okay, so I've got to fix that up. Oh no, I go to the next line. Okay, so lambda, rate of change, 1 over lambda dt is 1 minus omega over V minus delta K minus alpha minus beta. And that's now we're working in a reduced form. The previous thing was using actual values for Y, K, etc., etc. This is using ratios, but you'll find it's got exactly the same behaviour. So that's since I've got lambda hat here, lambda hat is 1 over lambda d lambda dt. So to make it into a differential equation, I model through multiplied through by lambda, I've got d lambda dt is equal to lambda multiplied by 1 minus omega over v minus delta k minus alpha minus beta. Now, the one for wages share, it's not quite as complicated. That's saying that's the rate of change of wages, and that's productivity. So I multiply through and say the rate of change of the wages share is the wages share multiplied by the slope of the function multiplied by actual employment minus the 0 point minus alpha. And that's a new set of equations. So if you want to make that into a Minsky model, you simply use the same sort of basic logic, actually with less variables to put it together. So that is defining lambda. You can flip the equations around, so I've made it possible to look at the matching here. Lambda is the integral, that lambda there is the integral of lambda multiplied by the growth rate, which is 1 minus omega over v minus delta k. We've shown that earlier, that that's the growth rate, minus alpha plus beta. Okay. So, next task, create a new model in Minsky and define this using the same constants we used over there where necessary. So the constants you're going to have in this one, you're going to have this one, you're going to have lambda s, lambda z, you've got all those delta k still there. We need an initial value for a, you need an a naught. Hang on, no, you don't need an a and d disappeared because we've got alpha and beta. So you need to have alpha and you need a value for beta at that point. You don't have k anymore, and you've got an initial value for omega, which you might say, if we make that 0 point, say that's 0.8, but that's meaning 80% of GDP is the wages share. Okay, so have a crack at that. And that's, you're going to be using a lot of the, to write alpha in Minsky is backslash ALTHA, beta is backslash BETA, and so on, and omega backslash OMEGA. Okay, have a crack at it. I'll do it live on screen while you, but don't look at me, do yours. I'm going to load the beta. The beta is actually better for designing new models. Oh, and here's a quick shorthand. I'll just actually make this a bit larger. Hang on. These things are still being fixed up in Minsky, but we're trying to make it easier to copy between models at the moment. So what I'd like to do is grab the definitions here that I want to make a copy of. So I need those four, and I need alpha and beta. But this is more complicated than it needs to be. We're fixing it up shortly. In the beta, if I want to select things, I hold down the control key. Okay, what's wrong? This is not the beta. Okay. Having selected them, put them in the same area, I'm going to group them. So I right click and left click and drag a rubber band around them, and then I choose group. Hang on. Choose group. The grouping is a pain because you've got to change the scale to see it. Notice how it becomes transparent there. Make sure it's not transparent, and you get save group as, and I'm going to save that as parameters. it's more laborious than it needs to be. We're going to make it much more straightforward in the later version. So I'm going to quit out of that without saving my changes. And now I'm in, this is now in the beta. Okay. So I'm going to file, open. There's several ways to do this, but file open works okay. Parameters Goodwin. And there are my parameters. I don't need to redef through to find them again. And I think that's all I need.
So you mean in the beta version we can use this group function?
Sorry, pardon?
In the beta version we can use the group function?
Yeah.
I think it doesn't work in mine.
A grouping works in all of them. What you do make a group, you just run a rubber. You hold the mouse key down and drag, and then in the space between them, you right click and you choose group, and then you get one of these things forming. Okay, grouping has still got a long way to go before it works properly. So I tend not to use grouping. I'll show you other tricks there. Yeah. Yeah.
Do alpha and beta have a value?
Yeah, make it larger so you can see them here. 0.15 and 0.2. 0.02. 0.015, 0.02. So I want an integral. I'll make that omega. And another integral. Lambda. I want lambda 0. And omega 0. Pardon?
That's 0.7.
Oh, I'm mucking around. It doesn't really matter all that much. It'll still work. Now those equations, you need to see the equations, don't you? In a second, let's bring them up on screen over here. So those are them down the bottom there. Where's my mouse got to? Those two. So those are the two equations to put into Minsky.
So we need to get. Okay, so let's go back to the. No. So okay. Open. Yeah, but I just create
Okay, yeah, okay, yeah, okay, yeah, that's fine. So this was did you agree with it?
No, I just delete this.
Okay.
You hold the control key down in the BD, you can select a lot of objects at once. Wait until they're all grey, then click in one and drag. And as I pointed out beforehand, if you want to add two things together, you can drag them to the same input. And what I'm doing, because they're both going to the minus key there, that's going to give me alpha minus alpha plus beta in the equation over here. Which I still haven't finished wiring up. Let's finish wiring it up. Now see the equations. That's saying d lambda dt equals lambda multiplied by 1 minus omega over v minus alpha plus beta. And I forgot the delta k, so let's go back and put the delta k in there as well. Copy that. Flip it around. Actually, I can also, one that I think is worth doing perhaps is defining a growth rate. No, I'll do that later. So that's the correct equation.
Yeah, it seems like it does.
Now I need to define omega.
You kind of copied the book, so what?
Yeah. I think it's, I don't think it's supposed to be the way it's Maybe you can. Maybe you can delete it. Maybe not.
I'm not sure. I should try. No, can but
Oh.
no.
Oh no.
But is it? I think this is interesting. Yes.
We are often good as artists.
The best.
So now we've got the first step. The technical step is our thinking. So you do the math.
Yes, of course.
Omega dt equals lambda s multiplied by lambda z minus alpha. Okay, that's correct. Now I know I've probably done it faster than you guys have done, but I'll give you a copy of this in a second as well. Well, let's just see how this behaves. Let's graph omega and lambda. And let's graph them against each other as well. Here we go. Okay. So the same basic behaviour, I'll actually say this now as Goodwin reduced form, which is one way to describe hang on, let's go to save. Oh damn, I saved over parameters, that's okay. I'll save as. Okay, and I'll give you all a copy of that. Now you can fine tune that later, you can do it yourselves as well. But that's showing again, deriving straight from definitions and using the simplest possible definitions, nothing complicated. I get a system with an unstable equilibrium and cyclical behaviour. And this is what neoclassicals think as exogenous shocks to an equilibrium system. Okay. So this is better founded than neoclassical models. I'm not jumping over any Sonnenschein Mandelbrot type problems. I'm working from macroeconomics to macroeconomics. You don't need micro foundations for macroeconomics. Okay?
What are the foundations again?
Macro itself. You're simply saying the macroeconomy has a structure, and the structure includes effectively class system, workers and capitalists, distribution of income, and the bargaining power of workers being affected by the rate of employment. And so put that together, you get a cyclical model. And neoclassicals that get their nickels in a total twist trying to explain why there are cycles. Okay? Having to bring exogenous shocks and all sorts of other nonsense in to explain the cyclical behaviour of the system, which emanates very simply out of the macro definitions themselves. Okay? And even if they built a model like this from the outset, and they build a complicated, so-called Cobb-Douglas production function, which is not a production function at all, when you look at the proper mathematics of it. It's a nonlinear mapping of the income distribution function. That's what it is. And that's, if you look at by Anwar Sheikh and McCombie and Felipe, you'll see that it's just a redefinition of wages equals wages plus profits, with relatively stable income shares. That's all the Cobb-Douglas production function is. But even if they did that, you could reduce their model to this and say it's inherently cyclical. So get used to it. Capitalism has cycles. And partially, one reason I want to put a growth rate inside there is that the growth rate of the system in equilibrium, if you could reach equilibrium, is actually higher than the growth rate out of equilibrium. So the cycle behaviour is not a cycle around an equilibrium growth rate, it's a cycle below an equilibrium growth rate. I'll give you a model that illustrates that shortly. So cycles do have real effect, and that's one reason why you try to reduce the scale of cycles, to reduce the level of unemployment and unused resources and low investment during a slump. Okay, so it has a policy implication that every living system is cyclical. And this is it's so painful to talk with neoclassicals, is that they think everything has to be in equilibrium. If you guys were in equilibrium, you'd be dead and at absolute zero, so you weren't decaying. Okay? You have circadian rhythms. You have all sorts of rhythms in your body that are part of why you stay alive. So everything is inherently cyclical. That's just, the natural systems are cyclical, and the economy is an extension of a natural system. Okay, we've built this as, rather than being plants or predators chasing other animals on the plains, we've built a production system on top of the biological world in which we live. We're an extension of that. We're also cyclical. So it's just quite natural to have cycles. The question is, what's the mathematics of them? So this is getting slightly more complicated. That's a more complicated version of the model I've shown you. Not more complicated, just more elements there. So I'm showing the wage change function, which is a straight line. There's the employment rate, there's the rate of change of wages, your cycles, growth rate as well, and the limit cycle of the employment share versus labour productivity. All I'm doing with things like this, by the way, is defining functions. That's the growth rate, that's the Phillips curve, just defined down here. So once I've defined like lambda s multiplied by lambda minus lambda z, I can call that delta wage function, and I can use that delta wage function somewhere else. And if I want to have a linear versus a non-linear function, I can have a logical switch there to change between the two. All this sort of stuff is just to make it easier to try modifications and extensions of your models at a later stage.
Have you ever had a discussion or exchange with a neoclassical on this?
What, sorry?
Have you ever had an exchange with a neoclassical on this Well,
They-
let me prove to you that you don't need microformations, and I start from just definitions macroeconomic.
I do occasionally, but normally neoclassicals don't come to presentations by post-Keynesians.
Yeah, sure.
The other way is not true. I've sat through more neoclassical presentations than I would. I've wasted a large amount of my time listening to neoclassical papers, but they don't waste any of their time, or they don't improve any of their time by listening to post-Keynesian ones. So it's a one-way street.
Yeah.
It's one of the frustrations in the literature as well. We cite them all the time. Our citations improve their citation ranking. I would like to have a dislike citation, give them a negative, because I've cited Bernanke so many times on arguing that the debt deflation theory of Great Depressions doesn't make sense. Bullshit, he's wrong. But every time I cite him, he gets an extra citation. Very frustrating. Anyway, so just showing you some other elements now. You've seen the equations tab in Minsky over here, which shows you what your equations are. That's just a bitmap. That isn't something you can actually put in a document. But on the file menu, you see one of the options there is export canvas, and you actually have three choices. I don't like how this is done. I want to change this at some point. One is an SVG file, and that's a vector graphics file. So you can. That's why I embed that in the program. I simply save the thing as an SVG. That gives me a vector style map of the model. I can then cut and paste that into a Word document. But one of the other options is LaTeX, and that outputs a set of equations. And those set of equations. Who's the LaTeX user here? Okay, good. Okay. Well, you can just load it straight into whatever program you're using then. Here we go. So there's a LaTeX document. Okay. So you could use it straight away. Others are stuck using Word, which I still am at the moment. What I tend to do is I'll grab, like this statement here, which is the definition of lambda dt, grab it up to the section where Word can interpret what I'm looking at. Go to a Word, like I can use Word or I can use PowerPoint here. I've got math type, paste it in, there's my equation. Okay? And that's publication quality formatting. So you can use this to document your model as you keep on working. And then when and I do a bit of editing and so on. So that's how I produce, high quality graphics to explain what's going on in the model in a mathematical paper. Quite straightforward. Now, systems properties. What are its equilibria and why aren't they stable? Well, this is going to be slightly mathematical. Who's comfortable with math? Who's uncomfortable with math? Okay. It looks complicated. It's really what one of my mathematics lectures called money for old rope. Once you know what's going involved, it's just a very mechanical process to work this out, and that's why quite a few mathematics programs will actually do the work for you. So to work out the equilibrium, you have to say, well, what values of lambda and omega are going to be such that d lambda dt and d omega dt are both zero? And we're now looking at proportions where these can be equal to zero while the economy is growing. Okay, because it's the proportion, the employment rate, the wages share, a constant while the economy is growing. So it's a growing equilibrium. Well, you define lambda e and omega e, and those are the equations for them. Now there's two solutions. One is where lambda e and omega e are both zero, and the other is where, when you work out the equation, omega e is equal to 1 minus v multiplied by alpha plus beta plus delta k. That's going to be less than 1 because v is about 3, alpha and beta are about 0.04 together, delta is 0.06, that's about 0.9, 0.8, in that region. And omega e is alpha divided by lambda s. Now alpha is about 0.0102. That's divided by 10, it's quite small, added onto the zero level. So the equilibrium employment rate is higher than the level at which wages are constant. Okay? So having done that, you now say, well, what's going to be the stability of this? Well, as I've emphasised several times, the stability of a nonlinear system is determined by its linear components, near equilibrium. The closer you get to equilibrium, the more the linear components of the model dominate the nonlinear. So it's the properties of the linear bit that tell you what's going on. Now, you linearise it by taking the matrix version of a Taylor series. Who's done a Taylor series expansion? Who knows what a Taylor series expansion is? Okay. It's a way of converting a function like sine or cosine or log or e to the x into a polynomial. Okay. And you have an approximation process. So you start off by assuming that, let's say, for example, e to the x is equal to a constant plus a parameter times x plus another parameter times x squared plus another one times x cubed, etc., etc. And what you find is you differentiate each side of the equation, and it's actually your differentials divided by, as it happens, the factorial that'll give you the value of the parameters. Once you assume that's true, if there's no discontinuity that's going to disturb the equation, like e to the x is a constant function, okay? So you can approximate it with higher and higher order polynomials. What do you think of the first approximation of e to the x is? What's the constant for e to the x? What is e to the 0? 1. Okay, that's your first equation. Okay. Your second is the differential. What's the differential of e to the x? It's e to the x. Okay, but you evaluate it the next time. You get a 1 divided by factorial 1. And so you get a polynomial that is actually. I might as well do that if I bring up, so I can bring up MathCAD. Do I have MathCAD running? I don't. Okay, I'll bring it up here. This was my favourite maths program. It's been ruined by the current owners of the damn software, so I'm using a version which is about 8 years old. It annoys the hell out of me. Okay, but if I have e to the power of x, and I want to interpret that using a series and expand it, say, out to 6 terms, then a 6th order polynomial expansion, where's my scale? A 6th order polynomial expansion of e to the x is 1 plus x squared divided by 2, which is 2 factorial, plus x cubed divided by 6, which is 3 factorial, plus x4 by 24, okay? It's all factorial terms. And if you just want to see what that looks like as an approximation, let's just compare it and see how it ends up looking. If I graph x, say, out to 10 from 0, and I have e to the x as what I'm graphing there, then let's just make it a bit larger so you can see I've stolen a few ideas from MathCAD and how I've designed Minsky. Okay, and now let's see how it compares to this approximation. Pretty badly once you get past about 4 terms. If I actually limit this to, say, just up to the value of 4, then they're pretty close. Okay, and if I want a higher level, then I might go for 8. Okay, and that's actually, the MathCAD's not doing a very good job of displaying. That's 5040. Okay, let's just look out that far. Okay, so you can see it's a better approximation, etc., etc. So that's what's going on with the Taylor series. Now, the linear part of a nonlinear matrix model is called its Jacobian. Okay, because I'm differentiating with respect to x when I'm looking at a single variable. When I'm differentiating with a system which has 2 variables, then I've got to have one differentiated against the other. Okay, so what you get is a matrix what are called partial differentials. And that's the differential of y, lambda with respect, the function for lambda with respect to lambda, and the function of lambda with respect to omega. And then the function for omega with respect to lambda, function with omega with respect to omega. And that looks complicated, but that's, so long as you do the differentials in one direction, which is what I'm doing, I've got the differentials horizontal in this particular matrix, and the equations vertical, it doesn't matter which one I do, which way, I'll still get the right result overall, okay? So what I get out of that is a differentiation. So if I differentiate all that, let's take a look at it. Actually, I think I've dived in too quickly here. So I'm differentiating this with respect to omega. So with lambda, the lambda drops out and I've just got that term. Differentiate this one with respect to lambda, I get omega times lambda s. Differentiate that with respect to omega, I get minus lambda over v. Differentiate that with respect to omega, I get lambda s, yada, yada, yada. Okay? Now, that's messy, looking messy, but it's all a very mechanical process. So to work out the Jacobian, that's the symbolic Jacobian. What I need to work out stability is the value of that Jacobian evaluated at an equilibrium point. And to make it simple, I'm going to evaluate this as the 0-0 equilibrium. We've looked at the positive equilibrium. What if you're starting with zero employment and zero wages share? What happens? Well, you simply feed the values in. So omega there is 0, lambda there is 0. So you get 2 zeros on this axis, and you get positive values over here and negative value here. So that's your first point. You've now got, what you now have done is you've taken this complicated model with nonlinearities and so on, variables multiplied by variables, reduced it to a pair of constants. Okay? And what you then get, you say, well, what's going to happen to the system if it's a small distance from an equilibrium? The linear bit tells you. So you define effectively a linear equation saying that the rate of change of the gap between where we currently are in the equilibrium is this constant multiplied by the gap. The constant being a matrix which has these values, 0.0238, 0, 0, minus 0.602. Now how do you resolve that? Well, it depends on what's called the magnitude of the real part of the dominant eigenvalue. Blah, blah, blah. Okay. What that means is you can convert that into a quadratic using the rules of matrix mathematics. It's called, you take the determinant of a matrix involving a variable, x in this case, just for the heck of it, minus the real one, and you using the rules of determinant matrix addition and matrix multiplication, you get x minus 0.0238 multiplied by x plus 6.02. Now, can you tell me what the roots of that equation are? Okay, they're 0.238 and minus 6.02. One of those numbers is very negative. So if you think about it as a parabola, it's crossing the x-axis at just below minus 6. Okay. Now, if that were the dominant eigenvalue, the equilibrium would be stable. You'd very rapidly converge on the equilibrium. But it also crosses on the positive axis 0.238. And that means you can express that as an equation as e to the power of 2.238 times time. It's going to diverge very rapidly. So what this is actually what's called a saddle. Okay, it's stable on one axis, unstable along the other. Now, if you imagine you're trying to rest a ball bearing on a saddle, okay, you throw a ping pong ball. You throw the ping pong ball at the saddle. What are the odds? It's going to slide off one of the edges. Okay, so it's an unstable equilibrium, even though one of the axes is stable. So that means the system's going to move away from this equilibrium. It's unstable. So if you start near that equilibrium, you'll move away from it. Now, the other equilibrium, okay, those calculations. So a wage share of 71%, which is roughly what workers used to get. Okay, it's gone down over time, and we're going to have an explanation for that later. And an employment rate of roughly 60% of the population being where you get a stable level of employment. So the general Jacobian, again, that's showing that's exactly the same equation, just a bit larger so you can see all the terms. You evaluate it at that point. Notice where the zeros are now. They've been flipped around. You've now got zeros on the other axis of the matrix. Now, who knows what complex numbers are? Who doesn't know? Okay, all right, okay. This is the sort of stuff we should learn in economics, because any discipline analysing cyclical phenomena has to learn about complex numbers. What does that tell you about economics? Okay, by leaving out the reality that capitalism is cyclical and trying to explain its cycles by exogenous shocks to a stable system. They didn't even teach you the basics of handling cyclical systems, which are complex numbers. Now, these complex numbers are numbers involving the square root of -1. Now, it might sound ridiculous when you first hear about it, and the reason it was developed was that one of the big things we wanted as a hotshot mathematician back in the old days, like 1200, is solve quadratics. And you had quadratics which you could solve into two roots, you know, a minus negative root, a positive root, two positive roots, two negative roots, but some didn't have a solution at all. When you draw them as a parabola, they don't actually touch the x-axis, okay? So they don't have roots, so you couldn't resolve those. So I've forgotten which mathematician it was, said, let's pretend that there's a number called the square root of -1. And then with that pretend, what they call imaginary numbers, we can now break into quadratic into two linear terms multiplied by each other, and we can get a solution for that equation. That was done several hundred years before we discovered electricity. But it then turns out the behaviour of an electrical signal follows the behaviour of complex numbers, because you can map those complex numbers to sines and cosines, and also the exponential value. So this is showing that the system is inherently cyclical. It's saying you won't converge to the equilibrium because the real parts to the equation are given here, they're both zero. So the real parts are zero. You will, if you start a certain distance from the equilibrium, you'll always remain that distance from the equilibrium. You won't converge into it, but you'll cycle around it because of these eigenvalues, or these values in the parameters. So what we've done, and I think it's time to finish. What time is lunch? 12:30?
Yeah.
You can go a bit longer, but I think. Can you cope with doing a bit more? Okay, I'll dive. We'll get into the beginning of Minsky here. So what we've shown, you can derive. It's got good macro foundations, unlike Neoclassical, which have bad micro foundations and don't acknowledge it. We've derived it quite directly, and the macro foundations include the distribution of income, which is something that's missing from Neoclassical micro. You learn about a representative agent. You don't learn about a worker and a capitalist. Okay? They abolish class distinctions in their analysis, but in fact, the Sonnenschein-Mantel-Debreu theorem, when you look at it properly, really says you've got to aggregate, you've got to work at the level of classes. They simply ignore that and carry on with their own nonsense. You get cyclical behaviour, not equilibrium, and they've got real effect. I'll send you this particular model on a data stick. But once you work out the equilibrium, as I've done there in the previous to work out the eigenvalues, you can then say, well, if you actually happen to be at that point, what's the growth rate of the economy? It will be non-cyclical, and when you graph that system against the actual system, you find the cycles are below the equilibrium. So it gives you a logical reason to say, well, if you want to not have people unemployed and wasted resources and lower rates of growth, it's advantageous to reduce the scale of the cycles. So it's an argument in favour of some macroeconomic management if you can be successful, if you don't diminish other elements of the system. So again, it even gives a macro foundation for macroeconomic policy, okay, in a way that Neoclassicals can't do. So you've got a well-founded model, it generates endogenous cycles. How does it compare to real-world data? Now here I've got to make a confession. There's one red herring by a guy called Harvey, David Harvey. There's several David Harveys. There's one famous Marxist, it's not him. And he did a paper called Testing Goodwin, Growth Cycles in 10 OECD countries. Now, back when I was in my early academic period, I was the referee for this paper. And I was disappointed, wasn't pleased to find it didn't fit the data well. He said, so following Desai, he does a predator-prey model against these countries' data, and he found it not a good, the estimated powers poorly predict the centre of the cycles, and the restriction assumptions in terms of all profit being invested and so on are not justified. That second conclusion I'm quite happy with. But qualitatively, there are cycles in the data. It does seem to appear the cyclical bit. Anyway, so I had a table of 10 countries, all these various parameters estimated, Phillips Curve for each of these countries. And I was, I had to pass it because, the guy had done the econometrics, it looked valid. Anyway, about a year or two later, I wanted to do some empirically based work now, so I'll use David's Phillips curve. And I graphed the thing. And it was off the bloody scale. The numbers were just crazy. So I wrote to him saying, David, I've tried to use your Phillips curve and I get these crazy numbers. And he said, yeah, my apologies, I made a typical schoolboy error. That was his words. I worked in fractions and then published in percentages and forgot to convert back to fractions again. So his values for the Phillips curve, rather than being 0.6 for the equilibrium employment rate, was 60. 60 times the population. That's why I was wrong. Okay? Now, fortunately, friends of mine who are mathematicians, so that's a little comment about the schoolboy error, you'd think you'd want to correct that in the literature. No, I didn't have time to do it, so one of my best friends and a great mathematician, Matthias Grasselli, working with an honours student, did a proper testing, went back to look at the Harvey values, and of course now I'd already told them there was an error there. So they knew if they did it, they'd find that they got a far better fit to the data than they got in Harvey. But the same journal would not publish the full mathematical paper. The reason being the editors of the journal include Tony Lawson, who's a good bloke. I like Tony, good friend, but he's anti-mathematics. So he wouldn't publish anything with mathematics in it. So the paper they published lacked all the mathematical proof, and that's been published, I think, in macroeconomic now, but that's the actual paper going through the logic and showing that, yes, the Goodwin model does fit the data for OECD countries substantially better. Well, quite well, and certainly far better than the erroneous paper from Harvey. So it does fit the data. Now, at the same time, just want to cover one little thing. The neoclassicals are currently caught up in a big hullabaloo about the Phillips Curve. This is a paper by Roger Farmer, who's one of the directors of the group that's actually ended up funding my research into energy. Not Roger's subgroup of that, but anyway. So there's a huge hullabaloo about how the Phillips Curve just doesn't make any sense. Well, let's take a look at Roger's paper. Man Q. I don't know how the Federal Reserve fits in there. That's probably an error from Ed noted, I guess. Plotnikov from Maheshwari. Where's Phillips? He hasn't read him. Okay, and this is typical of the mainstream. They don't read the original references. They read a textbook version of a textbook version of a textbook version of the original and think they know what they're talking about. Now, if you go back and look at the original, you find it's got a far richer history. So that's the actual paper. I've embedded in the presentation. When I give this to you, you can just click on it and download the PDF file. And that was part of a research program involving these three papers, amongst others. Stabilisation policy in a closed economy, some notes on time fund forms, stabilisation policy as well. This was an empirical paper to back up an engineering model of the economy that Phillips was building. Phillips would have been the first person to build engineering-based software of economics, and engineering-based software using flowcharts as well, if he hadn't been misinterpreted and vilified by the economics profession. And Phillips himself has said if he knew what they were going to do with the Phillips Curve, he would never have done the bloody study. Okay? It was that badly handled. So he did use, unfortunately, if you read that article, you'll find he does have one point at which he implies there's a menu. He said if it seems that if aggregate demand were kept at a value that would maintain stable level of product prices, unemployment would be 2.5%. If it was kept at stable wage rates, unemployment would be 5.5%. So it implies a trade-off choice. It does imply a menu there. But he did that to justify a hypothetical nonlinear relationship in a dynamic model, which he'd simply drawn in one of the previous papers. So he'd drawn this relationship, and then he thought, well, he'd better check and see if he can empirically verify it. And he did find an empirical relationship of that nature. And it's in terms of the rate of change of prices, not the rate of change of money wages. It's a general term about wages and prices of raw materials, not just wages itself. But he looked at only wages again. But what he was trying to do is build a model like this. Now, does it look familiar to you? Okay. Engineering bringing to economics. That's what he wanted to promote. Instead, the neoclassicals and the so-called Keynesians at the time, who were Samuelsonians, they're not really Keynesians, they simply grabbed the menu. And if you look at one reason why that happened, it's pretty obvious to see it. Let's take a look at the, if I got a copy of the Phillips Curve here, I'll bring it up from the slides. Hang on. Yeah, I better bring it up from the slides. Let's go back a bit. I don't know why it does that. It should be loading. There we are. That's the paper. Now, if you take a look at the graph, he had to assemble his own data rate by taking data. Oh, that's dreadful. I better go back through a TIFF file. I haven't actually downloaded it properly from JSTOR. my mistake. Let's bring up Phillips here. Now, where am I here? Oh, bloody hell. I know it's there somewhere. I've got a TIFF file. Here we are. Okay. If we take a look at the document itself, you'll see that's the overall data he put together from 1816 to 1913. And what he did to make the models was pre-computers. He was working with a mechanically operated calculator he had to borrow from the secretary at the department and take home over the weekend. And he had, all these data points are individual years, all those dots. The X's are averages he used to give him just 7 numbers to fit to a nonlinear function. And he fitted it to a I think it's a hyperbolic to some extent. So then when that's the actual data. Then he went on and fitted it to data for later years. Let's see if I can find. Okay, so that's the actual curve. This is the data from 1913 to 1948. Now these 2 bits down here, he explained, were due to the Trade Union Council of the UK agreeing to a cost of living adjustment after the First World War. Then what happened? Churchill put the country back on the gold standard, prices plunged, and wages had to be cut. So you see, you can leave these 2 as outliers. 1940. What was happening in 1940? Yeah, okay, the war cut off access to agricultural products from Europe. But apart from that, he said it fitted the data really, really well. So people looked at that and thought, oh, there's a trade-off. And that was the interpretation taken to the Phillips curve. Now, in fact, what he was trying to do was to fit it into, let's go back and find a model which was cyclical. And if you wanted to keep it at that particular point, you had to control all sorts of other stuff. Okay? It wasn't that the system would just choose this point, it'll stay there in any static sense. But that's the way the Neoclassicals have interpreted, and now they say it doesn't work. I mean, they haven't read the bloody thing in the first place. So typical Neoclassicals. And here's Phillips in one of the earlier papers saying recommendations for stabilising the economy based on multiply models and comparative statics. He said, but it doesn't provide a firm basis for doing analysis for policy because the time path may differ from the equilibrium. Well, can't have that, okay? It's in Neoclassical, you ignore that completely. And secondly, the model itself is too simple to include price and interest rate effects. That's why he was building a more complicated set of models. So Phillips has been denigrated by people who haven't read him, and if they did read him, they'd find it wasn't just a one-dimensional thing. He used one dimension because he had about 60 or 70 data points, annual data, over about 50 years. If you want to fit the true nonlinear function he did, you'd need a massive amount of data, which he didn't have. But he had a second influence, was the rate of change of the unemployment rate. He said if the rate of change of the unemployment rate, well, the rate of change of the employment rate is high, workers might get higher wage demands than they'd get if it was low. Second factor. And the third factor, cost of living adjustments. So all the stuff they say that Phillips leaves out was in Phillips' original paper. And that's typical of Neoclassical scholarship. They just don't read the originals. So ignore all the chatter you'll see in the mainstream about the death of the Phillips curve. Believe me, I'm preparing myself for having to say that on stage in September in Scotland in front of some of these people when it actually happens. They haven't read the original. They're discussing third-hand equilibrium-obsessed versions of what they're talking about. So, okay, let's now go and have some lunch and come back and we'll start putting Minsky into Goodwin.